Welcome to another video in the LaTeX tutorials, a comprehensive series. The ring structures. In section 8.3 we will discuss this. Now a ring structure can be produced by the command /chemfig and then *6, and in parentheses I will define the number of sides. So if I want 6 sides, then it is 6, and here 1 2 3 4 5 6, and 6 will be here as well. So this command will actually execute the ring structure containing 6 sides, which is a hexagonal in other words. And here it is. So it will execute a hexagonal structure. Similarly, if I want to make this one 8, means 8 sides, then I will have to add 2 more here, and I execute this one, and it will be the 8 sides now. Now in order to make the benzene structure, then it is a hexagonal structure, but the alternate bonds are double. So I will mark this one double as well, like the side. This was the bond, then double bond, single, double, single, double. So this way I can execute the benzene ring here. And let's see. And here is the benzene ring. Now if I want to make it 8 sides, then I write 8 here, and then single, and then double, and then single, and so on. So I build this, and it will be now 8 sides with alternate double bonds. Similarly, a branched extension to the benzene structure can also be done like this. When I write chemfig 6, and it is, you can say, single bond, double bond, single bond. After this single bond, then means single bond, double bond, single bond, and then after this single bond we are having a bond single at 30 degrees. So this is single bond at 30 degree, then double bond at minus 30 degree, and then single bond at 30 degree, and then after this one we will complete the benzene structure, and which is here. So the 4 are here, 2 are here. So it is a benzene structure is completed, but in between in the parentheses we have inserted some extra commands here and extra bonds here. So this way this can be executed. Let me execute this command in order to confirm, and here it is. And you can see benzene structure and then the associated bonds. And 5, a complete ring with 3 atoms by the commands chemfig. This can be done. Now how it is executed? A, and then 3 is there. Static 3 means 3 sides will be there. And how will be those sides? Single bond with B, single bond with C, and C is bonded again with A here. So I will have to copy this, and I can execute this one, but at the moment you can see this example as well. Here this after C bond is being eliminated, so this bond has gone while the rest they are there. So we will execute both of them, and let's execute this one, and it is chemfig, and now here A, B, C. Now I can remove any bonds here, like I remove this one, Ni belt. So the bond between C and A will be no more there, and it is like that. Similarly, for nested rings, the command chemfig, this is executed, which will make a nested figure like this. Now how this is done? You see here, chemfig steric 5 means there will be 5 side shape. 6 means here will be steric 6 means 6 side shape, and 4 and 5 and so on. So let's see here. When it is 5, then 2 are here, but after 2 we are having a 6 side shape. This, the one which 2 are here, because it should be 5, A steric 5 is here. So 2 are here, and then another sequence starts, so its rest 3 are actually here, and then a parenthesis. So this parenthesis opens here, and this parenthesis is closed here. Similarly, steric 6. So 6 here, and after 6 there is only 1 here, and its rest 5 are actually here. They are 4, and then we are having them here. So 4 plus 2 are actually 6. Similarly, 4 and then 1 here, and they are associated. So some of them are being omitted as they are becoming the double sides like this. This one, so it was actually 5 here, but we see how many sides having 1, 2, 3, 4, 5. Now it's a 5 side shape, but this 5 is giant, means the fifth side is actually shared with the hexagonal here. So that one is to be combined in it, and then after it, it's a square, means a 4 side, then 5. So here 5, 6, 4 and 5 again. So this way we can mark the nested loop here, and we can execute this command in order to confirm this. And here it is. So they are being designed like this. One can play with this by decreasing them and changing them. In section 8.4 we will discuss the Lewis structure. Now we know that in order to execute the command we will have to write /Lewis. Then the predefined angles in them are actually used as 0 degree will mean 0, 45 will be equal to 1, 90 will be equal to 2. So with a gap of 45 degree, all these angles are predefined. Like 4 means 180, 4 into 45 is 180 and so on. An angle will be followed by a full stop for a single electron, and for a pair of electron we will have to write it with a colon like this. When I write /Lewis 0, 0 means it is 0 angle. The electron is at 0 angle, point its single electron with O. So it will produce the output like this. This is O, and it is having single electron, which is this dot, and it is at 0 degree to it. Now if this electron, the same oxygen is having 2 electrons, then I will have to write here colon, and 2 electrons will be here with this O. So they are at 0 degree. Similarly, they are changing, like 1 degree means it is 45. So it is at 45 angle here, and then this is the oxygen. Similarly, at 90 degree, at 135, then this one is exactly the opposite of this one, so it is 180 degree for this. These examples are actually here, so let me execute this thing with this command. So I will copy this and I will paste here. Now what this command means, oxygen will be with 2 electrons at 0 degree. And it is showing oxygen with 2 electrons at 0 degree. If I change this one to point, full stop, then it will be showing 1 electron there. So I can change the angle, means from 0. If I now move to 180, so it will come on the other side, but here 180 degree I will have to write 4 because it will be in the multiple of 45. So it will come the other side, and here it is. Similarly, a water molecule with a display of ions can be produced by this. If I want to show 2 electrons on at this angle 45 angle and 2 electrons at 135 angle, then I will have to write the old equation, which was the H52 with O this one, and in between I will insert the Lewis structure, and the Lewis structure will be like this. Now what this Lewis structure means? It is 1, so it means at 45 degree colon 2 electrons are there, and then at 3 is the 135 degree, this one, and another 2 electrons are there, and then comma and oxygen. So oxygen is associated with 2 electrons at 45 and 135 degrees, and rest of the command is actually the old command which we have already discussed. So this way we can incorporate the Lewis structure, means showing the lone pair and double electrons there. The ions can be written in a chemfig like this. If I want to write A bond B, then the usual command chemfig A and B bond B are written. But now A is with plus and B is with minus, so I will use the normal mathematical form here, the power and then plus and then the power and then minus. Similarly, I can write them in the subscript, and in the subscript there will be the same situation, that they will come down. Let's execute this command, and here it is. And let me remove this one as they are not part of the command. And here we are having the bond and the ions with them. Similarly, if I want to write them in the subscripts, then I will have to write the underscore here. Similarly, an underscore here as well. And I execute this one, and you see the A plus and A minus have come down. I can write instead of A plus here, let's say 1, and with minus here, let's say 2, and then it can have a 1 bond with B2, and here it is. In section 8.5, we will discuss how to write a chemical reaction. Now a chemical reaction is enclosed in scheme start and scheme stop. So for the hydrolysis of ester due to the presence of water can be written as, means we would like to have a reaction equation like this: R with C, double bond with O, and then OH, and it is added with ROH, and then the products we receive are like this and H2O. So here we will have to first write this thing, and we will write the scheme start, and then the reaction will stop when we will write scheme stop. So in between these two we are having this command till here, and then we give arrow slash arrow, and it is like this, the arrow is in this shape. Then we are having the other side, and then H2O, and then our scheme will be stopped. So this one we understand how this can be written. This is the as usual command we have already done. R is bonded with C at 0 degree, and then C at 30 degree with O, and at minus 30 degree with OH. So this we have already done. And then there is a normal plus, so it will be with slash plus, not directly plus, and then ROH, so ROH here, and then this is this arrow, and this arrow is in this shape, that it is going this way. It is not, you can say, returning like this one, means interconvertible. And then we are having R, which is bonded with C at 0 degree, and double bonded with O at 30 degree, and bonded with OR at minus 30 degree, slash plus, and then chemfig, and I will write H2O. So this H2O I have written with chemfig. It can be written without chemfig as well, but if we write this in chemfig, then it will be much resolved here. So let me execute this one, copy, and I come here and execute this one. So this is now the reaction. R this plus ROH slash R this and plus H2O. If, as I said, if I want to remove this one, the chemfig, and only write H2O plus H2O, then once I have started this bracket here, so where this bracket is closing, it is closing here, and then plus, and this one H2O, and the scheme stops. So let me run this to check this, and you see it has given error because it is saying that on line 24 we are having the dollar missing. So let's see here and come over here. Here this underscore 2 should be actually in the dollar symbol. Then if we write this in chemfig environment, then we don't need to put dollar symbol. But if it is not written in the chemfig environment and it is written in the equation form, then it should be in dollar symbols. And I run this, and now it has been executed. But here if I look to this one and this one, then there may be a slight difference, because this one is not, you can say, part of the reaction in that form. So let me do compare these two with you. Okay, I just enter here, and here I write this in chemfig environment. So copy, and in order to compare that what kind of difference will occur if we do like this. Now this one should be entered here in order to compare them. Okay, and here it is. Here you can see that there is not much considerable difference between H2O this one and H2O this one, but to write them in this form out of the chemfig environment, we will have them to use extra dollar symbols. So in order to avoid that one, we can write them in chemfig. But if we don't want to use chemfig here, then it is not, you can say, in a reaction form, so we can do the ordinary mathematics here. And similarly, Some of the typical arrow styles I have provided in the book, that if the arrow style is like this one we used. If the arrow is like this one, so it will have a cut on it like this. Similarly, different arrow styles have been produced, the interconvertible like this. These arrows can be written in the equation at this place. Here slash arrow, we can give a different shape of the arrow. I hope you would have learned how to insert chemistry in a LaTeX document. Thank you for watching this video and stay tuned for the next video.